So before I show you how to solve problems in the past paper, I would like to cover some of the basics, the fundamentals or the concept. The first thing is about a formula which you're already familiar with. The force equals the gravitational field times mass. F is equal to Em or F is equal to Gm. Now here I've got a mass m, and we know that every mass produces a gravitational field. I've shown the field in these arrows which are pointed towards the mass, and I have shown the circles at a certain distance from the center. The first circle here, this is at a distance of r1 from the center of the mass, and the second circle is a distance of r2 from the center of the mass, and the third circle is at a distance of r3 from the center of the mass. Now I have placed masses at various position. I have got a mass small m. This is also called as the test mass. Now I would like to know what is the force acting on this mass when it is kept at a distance of r1 from the center of the mass, center of this big mass, and also I want to know what is the force acting on this mass when it is at a distance of r2, and the force acting on this mass when it is a distance of r3 from center of the mass. I have also shown you the direction of the force. It is towards the mass, or it is in same direction as the direction of the field. Now this is what you will come across in the gravitational field chapter. Now the force on mass m in the gravitational field created by the mass m. So you have to use this these kind of sentences. So here the gravitational field is created by this big mass m. So you know every mass produces a gravitational field. Because we are considering this small m as a test mass, we are ignoring the gravitational field produced by this test mass itself. Now according to the formula, when the mass is at a distance r1 from the center of the big mass, the force, I'm going to write F1 is equal to E1 times m. Now E1 here, so this is the value of the gravitational field at that distance. So here E1 is the gravitational field strength at the distance r1. E2 is the gravitational field strength at the distance r2 from this center, and E3 is the strength of the gravitational field at that distance r3. Now the force acting on the mass m at a distance r2 is, according to the formula, F2 is equal to E2 times m. Similarly, at a distance r3, the force acting on the mass m is E3 times, or the gravitational field strength at that point or at that distance, times m. Now we are going to compare this equation F is equal to Em with the Newton's gravitational formula. So you know that according to Newton's law, the force acting between two masses which are separated by the distance r is g times the product of the mass divided by the distance square. Now if I apply this formula for the mass m when it is at distance r1, so we get F1 is equal to gmm divided by r1 square. Now we are going to compare these two. So the first equation says the force acting on the mass m is E1 times m, and this Newton equation says the force acting on the mass m is gmm by r1 square. So these two force must be same. So this is just two ways of writing the force acting on the mass m at a distance of r1. Now when you compare these two, this E1 equates to everything in here. So when you compare, you get E1 is equal to gm by r1 square. So this looks like the formula to find the value of the gravitational field at the distance r1. Now compare with the force F2, that is the force acting on the mass when it was at a distance of r2. F2 is equal to E2 and m, and E2 is the gravitational field strength at the distance of r2, and according to Newton's law we get F2 is equal to g, the big M, m by r2 square. So when you compare these two, so you can find that in E2 must be is equal to this bit, gm by r2 square. Likewise, when you compare this with F3, the force acting at a distance r3, you got, so from the very first equation you got F3 is equal to E3 times m, and according to Newton's law you get F3 is equal to gmm by r3 square. Now when you compare these two, you'll end up getting gm by r3 square. So E1, and you got E1, E2, E3. So E1 is nothing but the gravitational field strength at a distance r1, and E2 is also the gravitational field strength at the distance r2, and E3 is the gravitational field strength at distance r3. So you can generalize this and say that the gravitational field strength at a distance r from the center of the mass m will be gm by r square, where the g is the universal gravitational constant and m is the mass that is producing the gravitational field. So by comparing this simple equation F is equal to gm or F is equal to em with the Newton's law, we are able to derive, or it is one of the way to remember the equation for finding the gravitational field strength at a distance of r from the mass. So one of the most important thing in physics is you have to understand the equation. You should get the meaning of the equation into heart rather than memorizing the equation or memorizing the formula. So you know that the gravitational field is equal to gm by r square. So by looking at this equation, we can say that the gravitational field is proportional to the mass of the object and inversely proportional to the distance square. So you have to understand this concept, the proportionality. So it is proportional to the mass and it is inversely proportional to the distance square. So looking at this E is proportional to m, what it says is if the mass of the object increases, the gravitational field strength will also increase. If the distance increases, so you got r here, the distance increases, because it inversely proportional to E, the value of E will reduce. So you have to understand this concept. Now also when r becomes very large, the value of gravitational field tends to 0. Now I got few example here just to understand this concept. Here I got a mass, and you can think this as a mass, a spherical mass of radius r from the center. So the gravitational field E1 is gm by r square. This is the standard formula we just saw. I have doubled the mass. Now you know that gravitational field is proportional to the mass. So if you double the mass, the field strength should also double. Now if you just apply the equation E2 is equal to G, here it's 2m by r square, you still have the same radius, or I can also write 2 times gm by r square. But if you look at here, the gm by r square, now this is what the gravitational field strength for this mass m with the r. So if you substitute this value here, you get, for the mass of 2m, the gravitational field is twice or 2 times the gravitational field of E1. So one more example, I got a mass of 3m of radius r. Now apply this the standard equation. The gravitational field is equal to G times the mass 3m by r square, or I can also write 3 gm by r square, but this bit gm by r square is nothing but the field strength for mass m. So I can write E3, the gravitational field for this mass 3m is equal to 3 times the gravitational field of E1. Now here I've reduced the mass. Now think that the mass is half the size of this. So here the gravitational field is gm by 2 times r square. So again, this gm by r square is nothing but E1. So the gravitational field strength here is half that of the first mass E1. So likewise, I've got here few examples what happens when you change the radius or the distance. So here I got a standard object with the radius r. Now to find the gravitational field at a distance r, so if you look at this diagram, the distance r is nothing but the surface. So you can also say the value of the gravitational field on the surface of this object, which is gm by r square. How about this one, where the radius is, the mass is still the same m, but the radius is half, which is half of the original value. The first thing you have to do is just put this value into the formula, gm by r by 2 square, which becomes gm divided by r square by 4, and this denominator goes to the numerator here, which becomes 4 gm by r square, whereas gm by r square is the gravitational field for the mass with radius r. So by reducing the radius by 2, the gravitational field increases by 4 times. So here I got the distance increased by 2, and we know that the field is inversely proportional to the distance square. So it's very obvious that the field strength should reduce in this scenario. Again, you just remember this equation, gm by r square, the distance square. So here the distance is 2r. So to find the gravitational field on the surface, you put 2r square. So this becomes 4r square, and if you compare this, gm by r square is the gravitational field strength of this standard mass, which is, so this becomes 1/4 times E1. So by doubling the distance, the gravitational field will reduce by quarter. So I got one more example here where the mass is doubled and the radius is doubled. Again, some of these things you can solve this mentally. So you know that the mass is proportional, so doubling the mass, the field will double as well, and doubling the distance, the field will go by a quarter. So it is 2 divided by a quarter, so it is half. So the easiest way is put these values into the formula. So we know that the gravitational field is a gm by r square. So g m here is 2m by 2r square, or 2gm by 4r square, or this you can cancel by 2, becomes half gm by r square. So gm by r square is nothing but the gravitational field when the mass is m and radius r. So the other concept you have to be thorough is how the graph looks like. Now you know that the gravitational field is inversely proportional to distance square. Now this is the inverse law, and this is the shape of the curve you should get. So if you plot the distance versus the gravitational field, so you will get a curve like this. And in fact, so this is the distance. If you think this is the center of the mass, this is the point, that's the surface of the mass. So that's why the gravitational field, the value here is the value of the gravitational field on the surface. So this is the curve you should remember. So if you know the gravitational field is inversely proportional to x square, and in math, so you know how to plot the graph for 1 over x square, which is something like this. So again, this is applying the concept what you understood here. I've got Earth and I've got a moon, and assume that you are asked to show the variation of the gravitational field from the surface of the Earth to the surface of the moon. So assume that you got an object that moves from Earth to the moon. Now again, this is again simple. So what I got here is, if you forget, just for the timing, you can forget this bit. You can just ignore this bit altogether. Now here, we know that the gravitational field on the surface of the Earth is 9.81. So starting from this value, you get a graph that gradually reaches almost 0 here. Now I have called this as infinity. Now this is not infinity in a literal sense. So this is some distance from the Earth where the effect of gravitational field is negligible. So I can treat that distance as infinity. Now if you go back to the moon side, and assume that the gravitational field on the moon is 1.6, and this is the surface, this is the radius of the moon, and the value of the field on the surface is 1.6. But when you draw this curve, you have to be very careful. You cannot start this value from here. You can't start like here. So you have to know that, because this height, we got this as 9.81, and if the moon gravitational field 1.6, you have to show this on the graph also. You should make sure that the value starts from almost 1.6 in the graph. So here it starts from here, and the field reaches 0 almost at this distance. Again, you have to keep in mind, the size of the Earth is much bigger than the size of the moon. So obviously the distance where the gravitational field strength is 0 is much further away compared to the moon, because we know that the gravitational field is proportional to the mass and is inversely proportional to the r square. Because the mass of the moon is much lesser than Earth, obviously it will reach the 0 value at a much shorter distance compared to the Earth. So you have to understand this concept. There are a few problems asked in the past papers about this. Now this is the distance from the center of the Earth to the center of the moon, and here if you compare this onto the graph, you know that this is the point where the effect of the gravitational field due to Earth is 0, as well as the gravitational field due to Moon is also 0. So this is the point I have shown here. Now this is the point which is near to the Moon. You have to keep that in mind. So this is the net gravitational field at this point is 0. And you just have to, sometimes it's kind of a common sense, I would say. Now you cannot have a point here which will have a net gravitational field as 0. It's not possible because the Earth is much bigger than the Moon, and at this distance the Earth will have a gravitational field value which is not equal to 0. So if at all there is a 0 point here, that should lie somewhere near to the Moon. So you have to remember this, you have to mention this in your exam problem. Some of the simple problems I have seen in the past paper is something like this. So what is the gravitational field strength on the surface of the Jupiter? Now when a question like this is asked, you will find the mass of the Jupiter given as part of the question. You'll also have the radius of the Jupiter, and what you end up doing is a simple formula substitution. You know the gravitational field is g m by r square. The value of g is given in your formula book. The mass of Jupiter is given along with the question, and the radius also given in the question. You just have to substitute all the three values and get the value. Again, a question like this is also very simple. What the mass of Earth given? The gravitational field is 9.81 and the radius is equal to r. So you'll be given the radius, or you can find the radius of the Earth in your formula book, and this probably you have to remember the Earth gravitational field on the surface. You have to substitute the values here, g m by r square. Now you know the value of g, you know the cap value of the big G, you know the value of r. So this becomes like a simple math problem where you can find the mass of the Earth. Now one more question of this type: what is the gravitational field strength at a distance of 5000 km from the surface of the Earth? Again, this is also a simple a formula or a value substitution problem, but there's something you can't forget here. It says the first thing is the value is given in kilometer. You have to convert this into meters. Then this distance is from the surface of the Earth. This formula is equal to g m by r square. The distance is always from the center of the object, whereas in the formula here they are given the distance from the surface of the Earth. So what you'll end up doing is, to apply this formula, you must get the distance from the center of the Earth. Probably the radius of the Earth is given in your formula book. You just have to add the radius of the Earth. Again, you have to take that in meters plus the distance given in the problem, which is 5000 km, or convert that to the meters and find this. You get the final value of the r. Substitute this into the equation. You will get the value of the gravitational field. So put everything in this formula, you can find the value of the gravitational field. So next problem is about show the gravitational field strength going from the mass 4m to the mass m. This like we already seen before, like going from the Earth to the Moon. So in this type of problem, you have to be very careful when you use the scale here. Now again, you just have to apply some basic skills here. If you apply the formula, you get the gravitational field strength E is equal to 4 times g m by r square, whereas here it is gm by r square. Now it's very obvious the gravitational field strength is 4 times more than this. Now if you want to show this in a graph, and remember the shape of the gravitational field, this has got the shape of the inverse square, 1 by r square. You get this, and the most important thing here is the way you show the value of 0 here. Now because this is a bigger mass, the 0 here should be away from this bigger mass and near to the smaller mass. And also the way you show this, the starting point. Now I have just marked here 4 divisions, and this field starts from the 4th division, and you know that from this, comparing these two formulas, you know that the gravitational field for this mass is 1/4 of this. So that's the reason why I've started the gravitational field on the surface at this point. Obviously it goes with the 1 by x square and reaches 0 here. So I've also seen some problems where you are given the density instead of the mass of the object. I've got an example here. So you are given the radius of the object as well as the density of the object, and you have been asked to find a mass. It's not just finding the mass. Probably you have to use a formula where you need the value of the mass, and you must be aware of this formula. Density equals mass by volume. So from this you can find out the value of mass. It's just a matter of substitution. This is just basic like algebraic expression. So you got density equals mass divided by the volume, and when you do the cross multiplication, you'll end up having the mass equals density times 4 by 3 pi r cube. So probably now after you find the value of the mass, you'll be using the mass value in some other equation. It could be to again to find the gravitational field at a certain distance. Some other variations are, you are given the density P, also a density, you are given the mass, and you have been asked to find the gravitational field G, and you know that G equals capital Gm by r square. Now in order to find the value of G, you must know all the values for on the right side of the equation. So you are given this, and probably you are given this as well, and you don't know the value of r. Again you can use the density mass formula. The density is given to you, and the mass is given to you, and this is the equation for the density. So density equals mass by the volume. By doing the cross multiplication, you can have an equation for r. Again, this is a basic algebraic expression, and once you get the value of r, and you can go back and apply the value of r in this equation to find the value of G. So some of the things you have to be careful is when you start using these type of calculations, you'll end up getting lots of decimals. So you have to make sure you use the correct significant numbers. So most of the time the number of significant digits you use here will be based on some numbers you will find in the problem. Now with this background, now I'm going to show you some of the problems from the past papers.